All right, so section 11.5 continued, more on lines and planes in space. Now we're going to start talking about how do we sketch a plane in space. So sketching planes in three-dimensional space. And to do this, we are going to use the intersection points that the plane makes with the axes. So we're going to find the intersection points of the planes, or of the plane that we're sketching, of the plane with the axes, and the lines of intersection with the coordinate planes. All right, these lines are called the trace of the plane in that coordinate plane. So these lines are called the traces of the plane in the respective coordinate planes. Okay, so something to keep in mind about the equations of planes: if a variable is missing from the equation of the plane, then that plane is parallel to that variable's axis. Okay, so for example, if I give you an equation that has x and y in it but no z, and I say, hey, that's a plane in space, that is a plane parallel to the z axis because there was no z in the equation. If two variables are missing, then it's parallel to both of those axes, meaning it's parallel to that coordinate plane. So if two variables are missing, the plane is parallel to the corresponding coordinate plane. All right, okay. Okay, so let's do an example. Let's actually try to sketch something here. So let's sketch the plane, this is my example, given by 3x plus 2y plus 4z is equal to 12. So let's begin by finding the various traces. So the xy trace is when we have z equal to 0. So that's going to be 3x plus 2y equal to 12. The xz trace, where y is equal to 0, that's going to be 3x plus 4z equal to 12. And the yz trace, where x is equal to 0, is going to be 2y plus 4z equal to 12. All right. So we can go ahead and sketch those into each plane. So let me draw my coordinates here. So there's my y, my z, and of course x is coming straight out towards us, so we'll draw that at some perspective there, not z, x. There we go. Okay, so we can sketch these simply by finding the intersection points with the different axes. So for the first one, 3x plus 2y is equal to 12. That line is going to have a y-intercept of 6 and an x-intercept of 4. So remember, to help maintain perspective, I recommend making the hash marks on the x-axis a little bit closer together than you do on the y and the z-axes. Okay, all right, so we have this right there. Okay, so that's the trace in the xy plane. Now let's look at the xz trace. So that is going to have x-intercept 4 and z-intercept 3. Okay, so there's that trace right there. And finally, the yz trace, it's going to have y-intercept 6 and z-intercept 3. And we have it here. So this is a sketch of our plane given by 3x plus 2y plus 4z is equal to 12. Now, of course, this plane is going to extend beyond just these axes, right? So you could, let me get another color here. We could kind of just extend this in this way. It's going to extend out like this, you know. And so it's going to be the plane that contains all of this here. But that's very difficult to draw. But it is fairly easy for us to see just this piece of it. So let me get rid of all that yellow that I just dumped on there. Oops. Come on, go away. Didn't realize I made that many marks. I'm gonna be here all day. Okay, so there we go. So this is a good way for us just to kind of indicate our plane. All right. All right, so now we're going to talk about some distances here. So now we're going to talk about the distances between points, planes, and lines. So let's begin by talking about the distance between a point and a plane. A point Q and a plane. Okay? So we're going to let P be a point on the plane. On the plane. N be a vector normal to the plane. And Q some point not on the plane. All right, then the distance from the plane to point Q is given by, here we go, D equal to the magnitude of the projection of PQ onto the normal vector N, which is equal to the absolute value of the dot product PQ with N divided by the magnitude of N. Okay? All right, so remember, the projection is going to give us that vector that is parallel to the normal vector from the plane to the point Q. Okay, so it's very, very difficult for us to pinpoint the exact place where that happens, but it's very easy for us to select any point in the plane and then find the projection of the vector from that point to Q onto the normal vector. Okay, so that is how we are going to find the distance from the plane to a point. So from the plane to a point. All right, so next up is the distance between a point and a line. So the distance between a point and a line. All right, so that's going to be given by D equal to the magnitude of PQ, vector PQ crossed with U, divided by the magnitude of U. Okay, where P is a point on the line, Q is a point in space, so that's the one we're looking for, the distance to the line, point in space, and U is the direction vector parallel to the line. The direction vector parallel to the line. Let's put a box around that. Okay, and then we can use these to find the distance between two planes, for example. So suppose we have two parallel planes and we just want to know the distance between them. We can find points on each plane and use these formulas to get there. So yeah, lots of practical applications. But let's go ahead and do an example just so you can kind of see that in action. All right, so let's let's find the distance between the two parallel planes, all right, given by 2x minus y plus 3z minus 5 equal to 0, and 6x minus 3y plus 9z plus 12 equal to 0. That is entirely illegible. Let me try that again. Okay, so that was 6x minus 3y plus 9z plus 12 equal to 0. There we go. I think that's a little bit better. Okay, so we're going to have to find those. So I need any point in one of the planes. So any point. So I'm going to choose 0, 0, and whatever z is, right? So we've got, oh, you know what might be better? Check it out. If I let z be the only variable remaining, when I solve, I'm going to get a fraction, 5/3. However, if I choose to let z be 0 and solve for y, I'll get a whole number. I get y is equal to -5. Do you guys see that? If you plug in 0 for x, 0 for z, then we're left with negative y minus 5 is 0, meaning that y would be -5. So there's a point on that plane. So now all I have to do is find the distance from this point in the first plane to the second plane here. So I'm going to have to find the distance from this point to that plane. So the formula I'm going to use is d is equal to the projection of PQ onto the normal vector, or the magnitude of PQ dotted with the normal vector divided by, the absolute value of PQ dotted with the normal vector divided by the magnitude of n. Okay, so recall that Q is our point in space, right? And then P is a point in the plane. So I'm going to need a point in plane 2, and I'm going to need the normal vector for plane 2. So the normal vector there is going to be 6, -3, 9, because those are the coefficients of x, y, and z. And then I need any point there in that plane. So again, I'll just choose, how about 0 for x? So this will be my point P. So 0 for x, 0 for z again. That will leave me with y equal to 4. So I have my point 0, 4, 0. Okay. So PQ, this is my Q up here, by the way. That's my point in space. So PQ is going to be the vector 0, 4 minus, -5 minus 4, -9, and 0. Okay, so make sure we're taking the components of Q and subtracting the components of P there. That's vector PQ. I'm going to dot that with n. So I'm going to get 0 plus 27 plus 0, which is 27, the absolute value of which is 27. So if I take the absolute value, it doesn't change anything. All right. Then the magnitude of the normal vector, so the magnitude of n is the square root of 6 squared plus -3 squared plus 9 squared. So that's 6 squared is 36 plus 9 plus 81. So that's going to be the square root of 81 and 9 would be 90. So that would be 126. Okay, so then the distance between these two planes is given by 27 divided by the square root of 126. Okay, and we can see that 27 is being divided by 126. So 126 is 14 times 9, which is going to be 27 over 3 root 14, which is going to be 9 over root 14, which if we needed a decimal, I would put a box around that, but if we needed a decimal approximation, we could find that that would come out to be approximately 2.4 units, whatever those units happen to be. So these two planes are approximately 2.4 units apart. Okay, so I think that covers just about the rest of this section. So apologies for having to do it in 2 goes, but we got it. And I'll have the next sections up ASAP. As always, if you have any questions, please do let me know.